Alright, this is going to serve as an introduction into rate laws because we're going to discuss rate law equation with regard to kinetics, and so we're going to go over what it is, how it relates, and how do we use it to solve problems. First of all, a rate law is an equation that relates the rate of a reaction to the concentration of reactants. It's actually a mathematical, and a catalyst is a mathematical relationship between concentration of just reactants only, to the rate of a chemical reaction. So you see reactants right there, only reactants in a rate law. They're raised to various powers, and that I'll show you how we determine that. In fact, we'll work on calculating that in class. The general formula for a rate law is you just write the word rate on the left-hand side is equal to K, and this is a constant that is temperature dependent. We'll get more into that later. And then you have reactants that are listed. Any of the reactants are listed in brackets because we use molarity. And they have exponential powers, and it's basically related to the rate of a reaction and the concentration. It's a mathematical relationship linking the rate of a reaction to, in this case, NO2, and the rate of a reaction to F2 in this equation, or not in this equation, but in this rate law. So this is what a rate law looks like. Just has the word rate on the left side, has K, and then concentrations of only reactants. The key thing is these will have exponents which help determine the mathematical relationship between the concentration and the rate. That's the key thing that you need to know. It's a constant, a proportionality constant, that is the relationship between rate and concentration. Biggest thing you need to know off the video today. Well, when we go to do it, if you look, we write it out as rate is written on the left-hand side, K is the constant. We just write K for right now. And then we have reactant A is there. Reactant B is there. In this case, C is a catalyst. We do include catalysts in rate laws. You can have a catalyst listed right there. The exponents, these exponents are what's key. We're going to determine the reaction order, which will help us find units for our constant and help us do other calculations. Those are determined only by experiment. If you only pick up one thing today, realize that they are experimentally determined. So exponents, and we're going to learn how to do this. It's the method of initial rates, are determined experimentally. So you have to mix things together, see how they react, see what the reaction rate is, and that's how we determine them. They are not obtained by looking at the balanced chemical equation. You can't take the coefficients, the little a, the little b. Notice they're not up there. It's m and n. It's because it's determined by experiment only. So rate law comes from experiment only, and we'll see how to do that. So if we look, we talk about what the reaction order is. What does that mean? It means it's the exponent concentration of a species in a rate law. So you can do a reaction order for each of the reactants listed in the rate law, say what its order is. All that's asking you is what is its exponent. So it's asking you what is the exponent in the rate law. That's what its order is when we ask what a reaction order is according to a reactant. It is determined, again, experimentally, third time I've said it, and it's placed in the rate law. How do we find the overall order of a reaction? Is by adding them all together. So all we're going to do is sum all the exponents together to get the what we call the overall order of a reaction. So we basically sum all the exponents in a rate law that we determine experimentally, add them all together, and that's how we find out the order. So if we look, take this reaction right here. Notice the reaction right here, we have coefficients, 2 and 2. Notice the coefficients are not the same as the rate law exponents because they're determined experimentally. This one happens to be the same right here. So this one happens, the 2 happens to be there. It's just by chance. This has been determined experimentally. So what does this mean? Well, when we look at the rate law, here's what it looks like. We say with respect to NO, we say it is second order. With respect to H2, technically the exponent there is 1. We say H2 is first order, and we would say the order of the reaction overall, based on the rate law written out, is it is a third order reaction. That's basically the reaction overall. So overall, the reaction is a third order reaction. So when we look at rate laws, we look at that, and we can use them mathematically, plugging in numbers to solve various little calculations, simple calculations that I'll show you. All right, so if you look, one thing is this would be a 0 order. Notice there's no concentration shown. That's why it's called zero order. First order, if you notice, the exponent for A, the overall reaction will be first order. Why is this a second order reaction? Well, A can be squared, or it can be first order with regard to A, and first order with regard to B would equal a second order reaction. Third order reaction, you could cube it, or you get the idea over and over. Why do we care about these in chemistry? Because we can basically, well, here's an example. So if you look, we did this kind of earlier. If you look at NO, the rate law exponent is 2, so it's second order. This is first order. What is the order with respect to NO? We would say the answer would be, it would be second order. Just referring back to its exponent, which is experimentally determined. What is the order with respect to H2? In this case, we would say it's first order. What is the overall order of the reaction? Well, 2 plus 1, we're going to say the reaction is third order overall. Then finally, what if NO is doubled, what is the effect on the reaction rate? This allows us to kind of say what if mathematically. This is where we can use this with a little simple math. If we have our rate law right here, and I want to know what the rate change is going to be, they're telling me that on a double NO. So what I'm going to do is I'm going to plug a 2 in there for NO. So what it's going to be is this is going to be doubled. K is going to stay the same. And the value of H2 isn't changed, so we don't even have any impact. We don't even care about it. Then we just basically do this. We take the value. We say NO is doubled, so we basically square 2. The rate will go up by 4 times. It mathematically tells us what happens to the reaction rate. So in this case, if we double N2, the rate increases by 4 times. And all we did was take the value, plug it in the rate law, and use the exponents. That's the whole idea. Once you have the rate law, you can use the exponents to determine any change in concentration and their effect on rate. So if we look right here, here's a rate law right here. Rate is equal to K. Concentration of reactant A to the second order, concentration of reactant B to the first order. What happens if you double A? Well, kind of like the same thing we did in the previous one. So I'm going to double A. K is a constant, I could care less. B isn't mentioned, I cancel it. What's going to happen to the overall rate? The overall rate is going to go up by 4 times. So it allows us mathematically to figure it out. What happens to the rate if you double B? Well, go back over here. If I look right here, I'm now in the process of doubling B. It has an exponent of 1. A is held constant. K is a constant. What's going to happen mathematically to the rate? The rate is going to increase by 2 times. So the rate's going to go up by 2 times. Next thing is they could also have you change concentration. If they have you change concentration, same idea. It says what happens to the rate if you reduce the amount of B to 1/2 its initial value. So they're telling me I'm taking B and I'm taking to the 1/2 right there. A is held constant. K is a constant. Mathematically, what's going to happen to my rate? My rate is going to go down by 1/2. It's going to decrease. So my rate will decrease by 1/2. So it goes down by 1/2 because I decreased the concentration. So that is the beauty of a rate law. When you have the rate law, you can use the exponents. You can determine what happens if you increase concentration, like if you double A, double B, or you decrease the concentration, like taking the value of B to 1/2. And that's the key for using rate laws. Other key things you need to know is make sure that you know that they are experimentally determined. We do not use the coefficients from a balanced chemical equation. That does not work. Sometimes they may happen to be the same, but overall we have to do it by experiment only.